Good afternoon, everybody. It's a great pleasure to welcome Professor Philip Paré from Purdue University, who is going to talk in our DREAM seminar this afternoon on a project called Epidemic Spread with Transportation, Modeling, Inference, and Control. Let me just give a brief background. Excuse me. Professor Paré is an assistant professor in electrical and computer engineering at Purdue, and he received his PhD in ECE from UIUC in 2018. And then he went to Stockholm, where he was a postdoc with Kalle Johansson. We were just talking about that at KTH, the Royal Institute of Technology in Stockholm. He is has received a number of awards. In particular, at UIUC, he won the Robert T. Shem Memorial Award for Excellence in Research, and he was named a Mavis Fellow. He's also this fall a fellow for the inaugural Societal Impact Program at Purdue University. And Professor Paré works in network control systems and in problems of modeling, analysis, and control, and in particular in the area that he's going to talk to us about today, which is epidemic spread with transportation. So welcome and thank you for joining us, Philip.
My pleasure. Thank you so much for the great introduction and for the invitation. I'll share my screen. Perfect. Everyone can see that?
Yeah, perfect.
Great. So as Professor Tomlin mentioned, I am in the Elmore Family School of Electrical and Computer Engineering. I'm also part of the ICON Center, which is a new center that was launched in the last year and a half, 2 years, for innovation and control optimization and networks, trying to bring all the controls people across the university together. And yeah, today I'm going to talk about some work that has been carried out by my PhD students in the first year of my faculty position. And hopefully you find it interesting. And I mentioned this a little bit earlier, but feel free to ask questions if you're not sure what's going on and you want some clarification. And if there's like in-depth questions, so we can hold those to the end. But yeah, so as anything with in this domain nowadays, we need to, if you're going to do research in this area, you need to, we need to take the time to acknowledge the tremendous impact this has had on everyone's lives, both just our day-to-day lives, but also those who have been working tirelessly in healthcare and who have suffered so much in their health and or economically. And so I've been doing research in this area actually since the beginning of my PhD, but it became more relevant and a little more heavy and scary, honestly. And just kind of as we're in this sphere, we need to recognize that. So with that being said, we have an outline of the talk here. So we're going to look at a couple of different models and some inference for techniques that we developed for learning the underlying states of these dynamic systems from the data that's available, and how we can kind of look at some control and tying data into these ideas. So just jumping right in, the first model we're going to look at is an SEIR type model over a network. So we look at each node you could think of in our network as a subpopulation, and then it's connected, motivated by transportation. We'll think about flights and closer connections via ground travel as well, and thinking about how transportation is a propagator of disease. So we've been thinking of, and to represent these edges, we're going to have AIJ represent AIJ represent the strength of an edge from J to I. And each subpopulation, or in the last map that we saw, each city in that case, can be split into different subcompartments. So susceptible, exposed, infected, and recovered is what we're going to look at for this part of the talk. And the states that we look at are a proportion of the subpopulation that is in that group. So these states add up to 1 because you're looking at proportions, and we're assuming a constant population size. So what flows out of the susceptible proportion flows into the exposed, and what flows out of exposed flows into the infected, which we'll represent with X. Excuse me. And then what flows out of the infected flows into the recovered group. And so the parameters are, the sampling parameters are, the sampling parameter is H, and our time step is K, and the delay between the exposure and infectious states is this rate sigma I, for which could be different for each subpopulation I, and then we have a recovery rate gamma. And this infection level iota, section rate iota, is the function of a number of things. So we look at possible susceptibility or exposure from infection from the exposed population, which could maybe be smaller than the infection rate from the infected compartments. And then you could have different rates depending on which one you're looking at. And then you could have a different strength or connectivity between the infectious neighbors. And this neighbor set also includes yourself. So if we're looking at a subpopulation level model, we'll obviously have infections occurring from inside the population as well. And so the first thing we did was extend this idea to instead of just being one network, we wanted to look at multiple networks. So thinking about L being the set of transportation networks, and then you could have different spread rates as a function of which networks, and you could have different networks, which represented by this AIJ superscript L. So yeah, and this work was published in the Control Systems Letters, and was also presented at the American Control Conference this past summer. So we need some assumptions on the model for it to be well defined. Again, as I mentioned, the states represent proportions, so they need to stay in between 0 and 1 and add up to 1 for all time. So we need our sampling parameter pretty much to be small enough so that the model states remain well defined. And we're only going to have non-negative infection rates and edge weights. So you can't not get sick or get less sick from infected people. And so the first result is that if we have the initial conditions being sensible, namely that they're all in between 0 to 1, and they add up to 1 at the initial time step, then they'll remain sensible, or they'll remain in this domain for all time. Moving forward. So in some more in-depth analysis, or just a little glimpse of some of the analysis we did, we looked at the dynamics of the exposed and the infected states as a function of in vector form. So the matrix here is SK is a diagonal matrix with the susceptible states on it. The TE represents the transportation matrix for the exposed networks. And so we have beta EL is the infection rate, a diagonal matrix with the infection rates from the exposed states. And similarly, beta XL is for the infected states. And then we can have a different adjacency matrix for each transportation network. And then sigma and gamma are just diagonal matrices with the sigma i's and delta i's on the diagonal. So this state, as I mentioned, this matrix is capturing the dynamics of the E at exposed states and the infected states, and exploring how it behaves can tell us the behavior of the limiting behavior of this dynamics. So the maximum eigenvalue, we denote the dominant eigenvalue as lambda max superscript MK, and that's important for this next result. So it's a little bit notation heavy, but as long as we start in the sensible domain and we have an irreducible infection matrix for the infected state, which means that the underlying graph is strongly connected. which means that there's a path from one node to every other node in the graph. And if there's an outbreak, namely that there's at least a little bit of exposed or infected population in at least one node in your network, then we have the following behavior. The susceptible states will be monotonically decreasing over time, and eventually, asymptotically, the exposed states will go to 0 and the infected states will go to 0. And similarly, this dominant eigenvalue is monotonically decreasing as a function of k. And after a certain point, this rate will decay further enough that it'll be less than 1, and which gives the fact that the infected state will converge linearly to 0 for all k greater than that k bar. So what we're seeing here is that eventually the virus will die out, but the question is we need to look at how fast, and when k bar occurs. And to be able to connect this to real data, we need to be able to estimate the parameters from data. So in order to do that, we can rewrite the dynamics in this beautiful gigantic matrix here. And on the left, we have the difference between the states. And since the states are coupled, we only need to write 3 of the 4 states because they add up to 1. So S0 here, and all the S states just equal 1 minus the sum of the rest of the states. And we can, if we assume that the dynamics are, in this case, homogeneous, we also have heterogeneous results. But by homogeneous, we mean that these betas are the same, these spread parameters are the same for every single node in your network. So everyone reacts to the virus, every subpopulation reacts to the virus the same way. Then we can rewrite the dynamics in the following way. And if you have enough data to be able to write this equation in this form, and this matrix here is full column rank, then you can clearly uniquely identify these 4 parameters. And that's what this next theorem states. It says if you have enough data, have enough time steps, and you're able to write the dynamics in the way we have in the previous slide, then if the following conditions are met, pretty much if your data is rich enough, then you'll be able to uniquely identify the parameters of the spread process. And as I mentioned, we also have, this is for the homogeneous case, but we also have a similar result for the heterogeneous case. And we've also looked at in between. So if you split your nodes into different kind of types, so we have like, as we'll see when we look at the real data in a little bit, we look at splitting the subpopulations into urban and rural, and looking at how we can learn 2 sets of parameters, but not one for every node and not one set in total. So we have a quick question from Kate. It says, if even just a non-zero number of exposed people constitutes an outbreak, we can think of the E variable like asymptotic COVID cases. Yes, so this is a great question. And let's go back to the plot over here. Sorry, I didn't catch the question earlier. So if we look at just this picture here, we have S goes to E, E goes to I goes to R. So we're making the infection rate a function of both possibly the exposed and the infected. And if the beta E's, the betas that correspond to the exposed portion of the population equals 0, this is a pure SEIR model. But with that non-zero, we're kind of trending towards an SAIR model. But the difference is that for a truly asymptomatic state to be included, you would want also an edge from exposed directly to recovered. And we've done a little bit of work on this. I have a ARC review paper with Professor Bashar and Professor Carolyn Beck, where we've examined this case both in the non-networked and network cases. But we haven't gone through with as much as real data as we have with this case, because it's just hard to catch all these cases. And we'll look at the next part of the talk, estimating the underlying states. But if you can't catch them, it gets difficult unless you're testing at least randomly sampling a large portion of the population or everyone, testing everyone. But yeah, so it's close. It's like halfway between a traditional SEIR model and an SEIR model. Yeah, thanks for the question. Okay, let's jump to, so we've looked at the parameter estimation, and then we're gonna apply it to real data now. So we have collected a number of different data sets. And this is in collaboration with my co-PI at University of Minnesota, Professor Raphael Stern. And what we did is we collected every flight data for every commercial flight in the US. And this was collected from the Bureau of Transportation Statistics. We wanted to see how travel changed, not only how travel affected the spread of disease, but also how travel changed over COVID, or as a function of time over COVID. This plot here is actually showing that. It's showing the reduction in flights per airport. And this data is publicly available if you'd like to use it. In addition to that, we also had my collaborator had an undergrad go through and estimate the load factor, or how many people per flight there were, because United Airlines actually makes this information public. The day of flights, you can look up a flight and see how many people how many seats were open and how many seats were occupied. And so we estimated the load factor of all the flights in the Northeast region of the United States using this tactic. And we learned the parameters from the data, calculating in we looked at interaction between counties. So you could think of this as road travel, and without any airlines being included. And we learned the parameters from the real data. The dotted lines are the real data. So each county in the Northeast United States. And then the dotted lines are the simulations from the learned parameters. And then as I mentioned before, we split it into two groups. So we have the urban counties on the left, and then we have the rural counties on the right.
Philip, what are the different colors?
So each color corresponds to one county. So the solid lines, so like this solid yellow line or goldish line is the simulation from this one county, and then the dashed dotted line is the simulation, is the real data from this from the same corresponding county. And so each line, each pair of lines corresponds to a county.
But this is road travel, not air travel.
No, no, this is infection levels.
Oh, okay.
Yeah. So we're looking at infection levels using road travel as the transmitter. So
okay.
That is, if a county was sharing a border, they were connected.
Okay, all right, thank you.
Yeah. And then we added an extra layer, transportation layer on top of that, where we included the flights. And that's what the second plot here is we learned a new set of parameters, two sets of parameters, one for the urban and one for the rural. And as you'd expect, it doesn't change much with the rural counties because they don't have airports. But it did change the urban flights a bit, and it improved the fit. It's unclear exactly how much you're gaining and how much is just fitting the noise a bit, because we're just adding two more parameters to the system. So if you add more parameters, you're going to get a better fit. Typically. So it's unclear how good the model was in general and whether it actually captured this behavior. So the last part of the talk and it's unclear whether the numbers we were using, namely the counts of infections, actually represent the states. So kind of building off these questions, we kind of motivated the next two parts of the talk, namely, given the infection data we have, is that really the underlying states of our SEIR model or epidemic in general, and also, is this the right way to model flow of population to capture spread of a disease. So to answer the first question, we tackled this problem thinking about, motivated by the fact that just because you got a positive test on a certain day, which is represented by this paper from the Clinical Infectious Diseases Journal by triangles, that doesn't necessarily mean that's when you actually entered the infected state or even the exposed state. So here, X's represent, so each row here is a person, and the X's represent the day they showed symptoms, and the blue boxes are the days they were in the same like chalet or hotel in France. So you can see that this person started showing symptoms on day 1, on the January 24th, but they didn't get tested positive until February 6th. So there was a long delay here. And then this person presumably exposed all these other people, but when they started staying in the hotel was a different day, and they started showing symptoms at different days, and their testing date was very delayed as well. So we want to look at a way to capture this, capture the underlying states of the SEI of these compartmental models using some probabilistic techniques, and that's what we're going to look at now. So for this part of the talk, we wanted to think about an SEIR model where the delay we're actually going to capture in our observation model. So instead of having an exposed state to introduce the delay will be on the measurement. And the dynamics here are similar. What flows out of the susceptible compartment flows into the infected compartment, and what flows out of the infected compartment flows into the recovered compartment. And the parameters are pretty much all the same, except we're only having a single beta here. And we're not looking at transportation for this part of the talk. So the question is, given the number of confirmed cases per day and the number of removed or recovered cases per day, can we infer these underlying SEIR states for a given population? And this work was presented by my PhD student Sion Zhang at the Mediterranean Conference on Control and Automation, and is currently in revision for TCNS. And so the idea we wanted to introduce here was trying to look at a probabilistic model of the delay. So tau I is a delay here, and nu I is some constant factor. As you can see, for depending on different testing practices in a given population, there can be a delay, a fixed delay of when people actually get tested. So they might want you to wait 3 to 5. Currently, most people want you to wait like 3 to 5 days, and this can shift depending on the location you're at. It looked at the early time steps, the early days in France, as we saw there in that map, in that table. It seemed like they were waiting at least a week to get tested. And the second part here is yi is a random variable following the geometric distribution. So the probability of you getting a positive test on day phi is just pi multiplied by 1 minus pi multiplied by, it's raised to the power of phi minus 1. So the idea here is you get the probability of getting tested on a single day is pi, and that probability decreases as the number of phi increases. And yeah, so this, and we've started actually, and I have in the backup slides, justifying this choice of distribution with a number of real data sets. And so the question is, how can we connect the real counts that we get on infected positive cases and recover the SEIR states from that, or infer the SEIR states from there. And again, so CIK is the number of confirmed cases on day K, and DIK is the number of confirmed cases, removed and recovered cases at time K. So this is really important also, and we kind of gloss over this, but we just had a tutorial session at MECC, and one of the talks was, which is a new conference kind of in mechanical engineering field, but we had an epidemiologist give a talk, and she was talking about how even in the same region, there can be confusion, because like at Illinois, they count cases different than they count cases at UIUC. They count cases different than the Department of Public Health does. Actually, it's a public health district actually there. And so it looks like there's a delay, but Illinois counts when you get the test, and then as the number of confirmed cases, and the public health district counts it as the day the case is closed. So there's a natural delay of 3 days. And so someone inferred from this data that the university was causing this big outbreak, but it was really just the wrong way of counting the data and not comparing different data sets correctly. So there's a lot of nuance in this, and I think this is why it's really important to work with domain expertise, domain experts, people who have domain expertise when you're doing this, and working on any problem, honestly, because we can miss things. But anyways, so the number of active cases here is the cumulative number of confirmed cases minus the cumulative number of recovered cases. And so then we look at since we're looking at proportions, we can scale this by the population size, which we assumed was constant. And then the distribution on the number of recovered cases, we just look at a binomial distribution. That's a function of the active cases divided by the population and the hitting rate of the recovery rate. So we are able to show that if the number of the proportion of confirmed cases on a given day K under the assumptions of the geometric distribution is equal to the PI, where this is the probability of getting tested on a given day in the geometric distribution, as a function of is scaled by this the rate of change in the SI state, so the number of susceptible people, plus 1 minus P scaled by your last number of confirmed cases. So confirmed cases from K minus 1. And what we can take away here is that if we know how testing is being carried out, we know the probability of being tested, and we can measure the number of confirmed cases per day, then we can infer the states. So if we test from K T plus 1, T1 plus 1 to T2 plus 1, so we look at the time in this region, then we can estimate the state change in the susceptible levels in the following way, which is just solving for this delta SI in the previous state, in the previous equation. And then similarly, we can estimate the delta RI in the rate, 1 over the hitting rate, scaled by our estimated infection state. And to get the estimated infection state, we assume that the delta RI at the first time step is 0. And we also, given some initial conditions, if you know the initial conditions, then you can just update your delta S and your delta R. And we know, since it's a compartmental model, that the deltas have to add up to 0. So you can solve for the delta X. And then we can iteratively update these estimated states over time. And the problem with this is that we don't know the underlying truth, so we can't actually validate this algorithm. But we started looking at validating the geometric distribution assumption with real data, and we've done the following analysis on the error. So if we assume that you don't have any confirmed cases before the date you start testing, which is kind of obvious, and then the error of the inference algorithm at time K is given by the following. So we have that the error between your estimated state and your true state is equal to your error in your initial condition. So if how off your initial guess is in your susceptible state, minus the cumulative number of delta S's that you also miss. So T1, recall, is the day you start testing. So if you don't start testing early enough and you miss the people that flow out of the susceptible state up to that point, then that'll also be your error, which makes sense. And we carried out a number of simulations to illustrate this. So the red line here, this is kind of like a valley. The red line here indicates where the infection is pretty much, the error of the estimator is pretty much 0. So we see that we can actually correct for the error if we start testing too late. So if T1 is when you start testing, if you start testing too late, your error could be pretty bad depending on when you start testing. But if you adjust for that by changing your initial condition and compensating in the right way for starting late, then you can have pretty much no error. And so we can see on the sides that we have error that's linear in the initial condition, consistent with the result, and we have what looks like the inverse of the S dynamics, the susceptible dynamics, being the error in if you start testing too late. So if you start testing after there's no susceptible people left, then obviously you're going to have really bad error. So yeah, this is working towards this idea of thinking about the susceptibility levels and the infected levels and the recovered levels and how we can estimate those from real data. We're also incorporating work that we're hoping to submit to L4DC at the end of the month, how you can include false positives and false negatives in the test, and how you can actually use these kind of tools to design optimal testing devices, like optimal tests, and looking at the trade-off between accuracy and delay. Yeah, so now moving to the last part of the talk, we're trying to answer the second question was, is this actually a good way of modeling the flow of population for inside disease? So what we did here was we looked at some ideas that for an SIR model and for SIS model that looked at population flow as the propagator. So instead of just having links in between nodes, we're actually looking at each state has, each subpopulation has a susceptible, exposed, infected, recovered proportion. And they also have, and those dynamics evolve similarly. So whatever flows out of the susceptible proportion will flow into the exposed, and whatever flows out of the exposed will flow into the infected, and whatever flows out of the infected, out of the infected flows into the recovered, etc. But we also have travel. So we have the probability of traveling, given that you're susceptible, out of this state, out of this node I, and then there's a negative sign out here. And then we have the probability of traveling if you're exposed, scaled by the exposed proportion, and then the probability of traveling, given that you're infected, flowing out of this. And then over here, this last term is the flows that are coming in. So this is all the flows going out of population I, and these are all the flows coming in from population J. So the probability of traveling from population J, given that you're susceptible, scaled by the susceptibility level of node J. And then here is the proportion of flow out of population J to node I, scaled by the total flow out of node J. And then they're also scaled by the population size of node J divided by node I. So you can think of this as scaling. If you come from a really big town to a really small town, you're going to have a bigger effect on the population. And this also guarantees that the population size remain the same, assuming that the flows in equal the flow out, which we'll show in a second. So kind of to just pick this a little clearer, each node, if this was a 2-node graph, has a susceptible, exposed, infected, and recovered. And then you have a probability of traveling out of one node. And in this case, whatever flows out of the one node flows into the other because there's only 2. And then in each population, there is flow between the subcompartments. But we're not allowing exposed people to move into the infected compartment while they're traveling in between nodes. That's one assumption we're making. We're also assuming that we're introducing this notation gamma, which is the proportion of people traveling out of node I scaled by, so the total flow out of node I scaled by the population size. So it's the proportion of people traveling out, which is the same as the probability of traveling given you're in one state scaled by that state. So the idea here is that for the population size to be constant, we need the flow in to equal the flow out. We also, similar to the first model, need the sample parameter, H, to be small enough such that the dynamics remain well defined. And we also will assume a similar result to the one in the theorem, the first theorem, where instead of needing the graph to be strongly connected, we need it to be K strongly connected. So when you take the union over time, so we can have the edges changing over time, if the union of these edges for every time length of big capital K, if that graph is strongly connected, then that's what this assumption means. And under this assumption, this model has this interesting behavior. So assuming there's an outbreak possible, so there's either an exposed and or infected proportion in one population or one subpopulation node, then we have a set of asymptotically stable equilibria of an interesting form. So we're assuming this mixing is occurring, and it actually, even after the infection dies out, the susceptible and the recovered proportions reach a consensus behavior. It's initial condition dependent, but it turns out that every node will converge to some alpha level in the susceptible, and then there's no exposed and no infected, so it's just 1 minus the S star for each population. And we can illustrate that on this simple toy graph that we use as motivation, where if we have an outbreak and the susceptible proportions decrease in the following way, this is about where the infection dies out, but we see that the states converge to this consensus-like behavior. But we wanted to see, okay, how can we use this model for control? How can we change the flow, population flow out of a node and use that as a knob to mitigate spread? So what we did was, since the population sizes, we assumed they remained fixed, we kind of had to do a bit of a rudimentary controller where we scaled each flow in the same way. So we call this theta value as the flow restriction parameter. And if you just look at an on-off controller, this is what happens. So just kind of looking at a single node, and if you have different controllers, which are these dotted lines here, and the corresponding colors are for the corresponding infection levels or average infection levels in the network. So what we see here is that if you don't have any flow restrictions, so if the first controller is just you let travel flow completely normal the whole time, then you have this outbreak with a pretty high peak. If we cut down travel right away, we have the following behavior, and if we don't reopen it, then we see there's a small peak and then the virus dies out. But if we look at travel and we cut it at day 50, that's what this violet line is, then we see that we can lower the outbreak, or we kind of stop the outbreak for a little while, but it still reaches a fairly high peak. We flatten the curve a bit, but not a lot. And this last orange line is where we cut the travel right away, but we relax it when it seems like it's about to die out. And we see this significant second wave as a function of that. So it looks like when you just use kind of a rudimentary kind of on-off flow restriction on travel between different subpopulations, it doesn't actually, I mean, it helps, it flattens the curve, but you still can have significant outbreaks. So we were wondering, can you do something smarter? Can we look at some feedback and look at a controller that incorporates some sort of feedback? So what we did here is we wanted to look at the average infection level, which is X bar, and kind of adjust theta as a function of that. And so eta can be thought of here as a sensitivity parameter. So the bigger theta is, the stronger, the more reactive the controller is. And so, yeah, so this is the average infection level. And when we do that, what we see is, depending on how strong of a controller you have, so these lines correspond to different eta values, then you have different responses. So the first two controllers with no control and with eta equal to a really small value, they're actually on top of each other, and there's pretty much no difference. Oops, excuse me. Sorry. And then if as eta gets bigger, we see this flattening of the curve, and it actually, then you have a second outbreak. And it turns out that, oh, that is definitely the wrong one, excuse me. So you see the curve flatten when you have this flow restrictions, but there's still a second outbreak. And it turns out that when you take the integral under these curves, in many cases, as we can see in this heat map, this is the total number of recovered people. It actually gets hotter, so it gets a little worse. So you flatten the curve, but you're not actually helping that much overall in the end. So the number of sick people actually can even get slightly worse. So, and this is under a number of assumptions. Well, first, it's assuming that this model is any good, which is not completely clear. I'll look at some real data in a second on that. And then the second part is looking at whether, is a question of whether this could be combined with something else to actually help a lot. So in order to do that, we want to kind of add a rudimentary vaccine technique into this. And the idea here is that at day 500, we start moving susceptible people in directly to recovered. And so if we add that in with our travel restrictions, it turns out that we really significantly reduce this second outbreak. So, and it turns out that if you don't have a very reactive flow restriction controller, then you don't gain that much. So if you look at the last one, the corresponding second wave here was not much bigger than with the vaccinations. So from this model, we learned that not only the travel restrictions maybe by themselves aren't that effective, but when you combine it with other strategies, it can significantly help. And if you don't shut the travel down, the effect of the vaccines actually seem to be much smaller. And we can see that as you increase, where this is the total number of people that get sick, so it's the people that are flowing out of the infected compartment, decreases as you increase the strength of your controller, as we can see here. So the integral under these curves gets smaller. So yeah, in the last few minutes, I wanted to look at for completeness, we also look at combining the vaccinations with the on-off controller. And as we saw with the more sophisticated feedback type controller, this is without vaccinations, and on the right is with vaccinations. The second outbreak gets reduced significantly, but the sooner you start the travel restrictions, the better effect it has. So for the last part of the talk, I'll just touch on some real data, but it doesn't look like I have very much time. We've just barely started this and we're working on cleaning it up a bit, but the idea is looking at spread data inside Minnesota. So this is the infection levels in Minnesota. And again, we're looking at each county. So this is the number of confirmed cases per day. And so we estimated the susceptible levels, the exposed levels, the infected levels, and the recovered. There was a big outbreak in a southwest county at a meat factory. That's what this kind of big outlier here is. And we also had travel data between each county. And that's what this heat map is showing, a log scale of that travel data that was collected from a third party. And then we fit the data, and we didn't get a great fit on this first run, but the idea here was my PhD student was trying to match up the time. So we learned the data up to a certain point, and then simulated the whole, he used this as training data, and then simulated the rest of it, and was able to match up close the overall outbreak where the infection peaked. And then he used a smaller set of training data and was able to match the magnitude, because the magnitude on the last spot was way off, but the peak time is much later. As you can see, the X scale here is very different than the scale here. So we're still working on trying to clean up the data, and also thinking about how we can combine these results with the do better estimation of the exposed and infected states as a function of the counts that we got, combining the second and third parts of the talk. But in short, we looked at several models and several data sets, trying to fit and learn different model parameters and do some model validation, as well as thinking about control. And we illustrated strengths and weaknesses of travel bans by themselves and how they can help when combined with other strategies. For future work, I mentioned a little bit of this, but thinking about the asymptomatic cases and how to estimate those, and exploring these SEIR models that maybe capture COVID more accurately, incorporating testing inaccuracies when estimating the epidemic states is an ongoing effort right now. And then we want to look at more sophisticated model-based data-driven virus mitigation strategies, improving those. And we have some efforts going on in that as well. And I just wanted to say thank you and acknowledge my funding organizations, the NSF, as well as C3AI, which is actually a joint institute between UIC and I think Berkeley. Yeah. So thank you very much for your time, and I would be happy to take any questions. So sorry, it was a little, haven't left a lot of time for questions.
That's okay. Thank you, Philip. That was a great talk. And we'll open it up now to questions. Maybe I'll start. Yeah, and the Digital Transformation Institute is joint between Berkeley. I mean, I think the leadership is joint between Berkeley and UIUC.
Yeah, it's Shrikant and Shankar.
Yeah. I had a question. I really like the ways that you were able to kind of gather like existing data and kind of inject it. And you showed that near the end of your talk of looking at existing data and seeing, you know, if you could now look at, you know, identify parameters and then start to validate the model. So I was interested to see that. And also a question I guess I had is, when you start to talk about mitigation strategies, so kind of control, do you think that you have access to, or do you expect to be able to have access to observed data so that you can like basically use your observed data under some of these mitigation strategies? So actually, you know, there was maybe a travel ban in effect, and be able to go back and sort of, you know, without doing an experiment, be able to kind of test that causality hypothesis that, you know, here the travel ban, I mean, I think that's a big effect, right? So you're able to kind of see the effect on previous data of mitigation strategies that you're now looking at.
Yeah, so
to be able to validate.
We actually, with the PhD student I helped co-supervise with Henrik, we just submitted a revision to the International Journal on Robust and Nonlinear Control for a special issue they have going on. it was actually, we resubmitted the revision last night. And the idea there is we're looking at just non-networked case, thinking about how we can estimate the impact of different techniques or different mitigation strategies as a function of the data. So looking at whether as you measure data as a function of time and you're estimating the parameters, can you see what NPIs or non-pharmaceutical interventions have an effect? And we showed that as long as you have about 2 or 3 days in between the different interventions, you can show whether that had an effect or not. Mm-hmm. And which one actually helped. Because a lot of people, when you do 5 things at the same time, it's hard to tell which one actually helped, right? And so the goal there, well, part of the goal there for my side of the project was thinking, what I want to be able to do is kind of be able to undo the strategies and not only know when it happened and if it helped, but be able to figure out the difference it made so that we can figure out how we could have maybe done it better or what we learned or which ones were the best. And I think that's really, really important. We also have, speaking on data, I technically have data agreements with UIUC and Purdue who collected a massive amount of data. Illinois had mandatory checks, at least for fall, for everyone on campus every week, at least once a week. And then Purdue was doing like heavy surveillance testing, at least 10% of the university population for the first 2 semesters. And so still having trouble actually getting our hands on the data for IRB and VPN issues, but and like data security stuff, but we're getting really close and hoping to kind of take this to the next level and thinking about not only can we compare figure out how strategies affected the spread, but also looking at different techniques. So the testing everybody versus only testing part of the population. And thinking about testing in isolation as a control mechanism is another problem we've been working on with my joint postdoc Professor Sundaram's thinking about kind of learning-based model predictive control and how we can use testing in isolation as a mechanism to mitigate spread, as we've seen in many cases.
Okay, thank you.
Hopefully I answered the question. I talked for a while. Not sure.
Yeah, no, that's great. Are there other questions from folks on Zoom?
I have one question that is it possible to theoretically kind of theorize some confidence level of the control effect with respect to some data gathering in some period? For example, so in COVID, people are really struggling. So we cannot wait for 1 year to gather data and make a model and control. So but if you gather only 1 week or 1 month data, probably we can say confidence level of the modeling is not really high. So is it kind of a way to analyze the confidence level for this work?
Yeah, so I think I'm gonna stop sharing just so we can see faces a little better. Yeah, so this is great. This is a great question. So we do have confidence levels in this change detection paper that I mentioned in collaboration with KTH, but in this work we haven't done anything on that yet. And it's hard to you need a data set that's really clean and tells you when the strategies were implemented. But we also think that if you have a big change in a new variant, that these change detection can also be used for that, hopefully. We haven't validated that yet. We only looked at data in France pre-Delta, but that's something that I think is really important in thinking about. Not only can you see the effect of control, but also the effect of new strains of the virus, and because that's a key point and especially since there's a lag between, it seems like, Europe and the US. So can we use that as a prediction tool to be able to prepare ourselves? It seems like people won't learn and will always just be behind, but hopefully we can get better at this.
Thank you so much.
Any more questions?
Any other questions?
You only have 3 minutes to get to your next meeting for Berkeley time. So
thank you. Anyway, thanks very much, Philip. That was really interesting work and a pleasure to have you talk in the seminar.
Yeah, it was my pleasure. It was nice to meet you all. Hopefully we'll be able to be at ACC or CDC next year.
Yeah, start back on the conference circuit, hopefully.
Hopefully, we'll see. Well, thank you so much.
Well, thank you. Have a nice evening, and I look forward to seeing you sometime soon.
Awesome. Thank you all so much for attending, and thank you again for the invitation.
Thank you so much for your great presentation.